Okay, now we will talk about example 2, that is a textbook problem 2.15. Okay, consider a river flowing towards a lake at an average velocity of 3 meters per second at a rate of 500 meter cube per second, and this meter cube per second should be the volume flow rate. Okay, at a location 90 meters above the lake surface. Okay, and we need to determine the total mechanical energy of this river water per unit mass, okay, as well as the power generation potential of the entire river at that location. We need to find out the power that it can generate. Okay, so here I need to remind you something. This so-called the total mechanical energy, okay, let me remind you, that should be by the definition. Okay, let me write a definition here. It should be the total energy that can be completely converted to work. Okay, that's the total energy that can be completely converted to work. That's a definition of a total mechanical energy. So that if we would like to find out this mechanical energy per unit mass, let me write something down. We write out the definition first. That will be equal to P divided by rho plus V squared divided by 2 plus GEZ. Okay? However, this is not the whole picture. Why? Because as you can see, okay, suppose there is some fluid here. After it passes through these devices, it will get into the free surface. Okay? So there is no change in the pressure. So there should be no any flow work in this case that is available for providing the mechanical energy, so that this term will become 0. Then we will only have two terms. That's the kinetic energy per unit mass as well as the gravitational potential energy per unit mass. Okay? We can use only these two to provide the mechanical energy. So after we substitute some values, we will have 3 squared over 2 plus 9.81 times 90. Okay? And we will get this value, that is XX 7.4 joule. Okay, and if you take 3 significant figures, that will be XX7 joule. Okay, so we have found the total mechanical energy per unit mass. Okay, and the next thing we would need to find out the power generation potential. So how can we find that? Okay, we just use some of the formula we have before. That's here. This power generation potential will be equal to E dot. Okay, this E dot will be equal to the mass flow rate times the energy. Okay, the mass flow rate, as I've said before, this is equal to rho times V dot times E. Okay, this mass flow rate is equal to rho times V dot. Okay, well, you can think of that, we just dot M equal to rho V on two sides, and assuming that is incompressible, so that we will have M dot equal to rho V dot. Okay. And after that, we just substitute some values by knowing that the flowing fluid is water, so that we can substitute this rho by 1000, so that we have 1000 times 500 times what we have found before, that is the mechanical energy per unit mass, XX 7.4, and finally we get 443.7 times 10 to the power 6 watts. Okay. After that, we will get the value in 3 significant figures. Okay. And that's what we call the power generation potential. Okay. Of course, as you can see in this case, the energy power potential should be the limit. Why? Because we haven't accounted for any fractional losses. Okay. This 444 is the upper bound, or we call the maximum limit of this power generation potential. Okay, and that is example 2.